Our next speaker is Sebastian Böhm, so he is going to talk about PULCEO.
Okay, so thank you very much. Yeah, I'm Sebastian. I'm really happy to be here. Once again, it's my pleasure to present you how we integrated task scheduling and offloading in our cloud edge orchestration platform PULCEO, which stands for Platform for Universal and Lightweight Cloud Edge Orchestration. And with that, we are closing the research gap of bringing solutions, advanced cloud edge orchestration techniques, which are only tested by simulation, into real-world environments. So on Monday, we already had a talk about the compute continuum, cloud edge compute continuum, and that is exactly the research area where we're working in. But to give you a short recap anyways, I prepared the research problem on one side. So this is about task scheduling and offloading. And in task scheduling and offloading, you have a set of IoT, respectively mobile clients, and all of them are submitting independent and atomic tasks. And those tasks are characterized by properties and requirements, for example, CPU resources, memory, bandwidth, and also properties, for example, where should a particular task be deployed. And the usual procedure is we have the set of tasks T, it's submitted to a gateway. Yeah.
Deadline, also deadline?
Also deadline, yeah, so this is not complete, of course. So you will see that later in the model we derived from the literature. And those tasks are submitted to a gateway. It might be in the cloud, it might be in the edge, anywhere, depending on the solution. And it's then put into a queue, and then there's a particular scheduler. Yeah, so there are many scheduling policies, and the scheduler now tries to find a particular mapping between the tasks and the nodes in accordance to some particular optimization goals. For example, minimizing the deadline or minimizing energy consumption. So there are a lot of solutions. But the problem is, there are many solutions, but most of them very similar to the problem we presented last year about service placement of applications in the heterogeneous environment. There's limited reproducibility of such solutions and also general applicability, because most of the evaluations are done by simulations, custom implementations, and there are still missing real-world experiments. So for example, as shown by a study conducted in 2024, only 3 out of 36 solutions were using real-world evaluations. Now you can raise the question, is it necessary to do real-world experiments because they are cumbersome, they are costly, you may need to pay for cloud resources and so on. But the answer is yes, you might need those solutions. And that is not only my opinion, so I selected 2 papers here. So the authors were also developing a solution for task offloading. And for example, the first solution is saying where the value of the CPU weight and memory weight is an empirical issue and multiple experiments are required to obtain the optimal value, all parameters have been set. So just based on assumption. And also the second solution, FAIR, is a scheduling solution, requires update information on the clusters, including CPU, memory, and bandwidth usage. A real-world implementation should thus carefully balance. So consequently, yes, we might need real-world experiments also in that area, very similar to service placement. And therefore we derive the concept of holistic cloud edge orchestration. So this is basically, my PhD topic depicted on one single slide. So on the left-hand side we have the concept, this holistic management lifecycle. So we treat experiments in the cloud edge environment holistically. It's creation, that means creation of the overall infrastructure, that means fog nodes, edge nodes, then the operation, placement of services on particular nodes, then obtaining memory at monitoring values, for example, CPU utilization or memory utilization, and finally as well the evaluation and the documentation of the results to be shared with other researchers. And all of these operations can be done with one RESTful HTTP API, and this is so the platform that we have been developing in the last years. It's based on a microservice architecture, also in accordance to some standard and based on a survey paper which were investigating cloud edge orchestration solutions. Okay, and this year we came up with the following 4 contributions. So on top of that, what we have already done with service placement, we provide 4 major contributions. So the first one is we integrated task scheduling and offloading into that platform. Then we provide a general, universal and flexible model of tasks. The third point, we integrate already available task processing applications that some authors may have used already. And finally, we are stick to the principle and we provide automatic orchestration reports with a set of standard evaluation metrics. And that is the derived task model we derive from the literature. So we have a task, again, with a set of fixed requirements and properties. So for example, you can here find the deadline of a particular task, size of the workload, payload, and it's flexible because we want to be stick to the universal claim we had. So the name universal is in the name of the platform, so I assume it should be universal to some extent, at least, so you can just expand this model because we have maps with requirements and properties. Then we have some task metadata for additional internal routing information. We have a task scheduling entity that is storing the current state of the scheduling process. So for example, scheduler have made a decision, so where should the task be executed finally? And we have some task status log, which stores the state transitions over time. And one example lifecycle would be, so none, the task has been created on the IoT device. Then we have new, it has arrived at the platform, it's scheduled, that means a particular scheduler has made a decision to assign the task a particular node. It has been offloaded, that means the task has reached the target device and it's running, that means the target application has started to process the task and finally it's completed, of course in the base case, and there might be failed, but this is, for this example, it's not considered. Okay, now we come to our contribution, how we design the orchestration workflow. So this is just an overview. On the left-hand side, we have the platform. We integrated all the task-related functionalities into the service manager component. And there is again this RESTful API, so we have here tasks. And we have the decoupled scheduler. And the decoupled scheduler is just interacting with the platform using the API gateway. And on the other hand, it's just doing a publish and subscribe relation to an MQTT broker. And we have the Cloud Agent SOC node, and realize the Kubernetes and the node agent component we have. And internally, you can just place applications, and there is internal endpoint where the application can interact with, for example, to update the state of the current task to inform the platform, okay, what is the current state. Okay, so we have a scheduler, then we have for the experiments, we have different task types. So we consider, as most authors, small tasks, medium tasks, and large tasks. We have different batch sizes from 200 to 800, and we have different task sizes and also different resource requirements like CPU shares, memory, and so on. And for this first experiment, we used the instance of the already used Edge IoT simulator that we used the last time as well. And this is how it works. So we have an IoT device here, and it just submits the task, as in many other solutions as well, the task using a post request, and then it arrives at the platform. So here the service manager, and in the same turn, the IoT device is subscribing to some MQTT topic to get informed about status updates. For example, if this task has been scheduled, it has been running, or it was completed. Then it arrives at the platform, and the scheduler is now via MQTT informed, okay, there's a new task just arrived at the system, please have a look at it and perform a scheduler to the scheduling policy. And this might, whatever scheduling policy, based on machine learning, ILP, whatever you imagine. And then the scheduler is performing a put request, so it updates the scheduling entity of the task. For example, it assigns a particular node, and then the service manager is just pushing the scheduled task to the target node, again via a post request or via MQTT. Then for task processing, we have the interaction between the node agent and the application. So the task has arrived, and that now the node agent is pushing the task to the application. And then the application, after successfully processing the task, it can just update the task again. For example, as you can see here, the new task status is completed, and then finally the response is returned to the IoT device. So this is how the orchestration lifecycle looks like. So if a lot of interaction, this is necessary to obtain the telemetry in the end, because we need to know how many time was used for scheduling, how many time was used for offloading, how much time was basically used for processing and so on. Now to the evaluation. So from the literature we obtain two categories, task metrics and performance metrics, and similar to the service placement, it's included in the automatically generated orchestration reports. And just to show you a few examples, so this is how the task metrics look like. So what is really important is the overall completion time. You can see here on the bottom right corner, and then the drill down. So for example, the waiting time on the PSM means after the task have arrived at the PSM, how much time was spent. Then how much time was spent with waiting on PNA, how much was the offloading time, the waiting time in total, and also the processing time which was used by the target application. And of course, there's some overhead caused by HTTP. It's a heavyweight protocol, but if you look at the research papers, most of the authors, if they use real implementation, they use HTTP even in the edge IoT fog environment, and if they're not, they recommend, for example, using HTTP or MQTT as communication protocol. And of course, for the telemetry and for the proxied application, as you can see here. So the application here is running inside the fog node. So this is necessary because most of the applications which are out there, they don't have any security mechanism. So they would be exposed publicly, and with this method we just have a secured proxy, and you can easily integrate the application, run the application without any security issues. That's the reason we have made this design decision. Regarding the overall performance metrics, interesting for the overall scheduling process. So most importantly is the task response time, because in the Cloud Edge environment we are interested in, well, reducing the response time overall. So you can see here the task response time, the time that were used between submitting the task and getting the response back. Then the task arrival rate, so how many tasks are arrived at the PSM for a given interval of time, and of course the throughput, so how many tasks could be successfully processed, could be successfully completed by the system over a particular interval of time. And in this case we performed 3 runs for the experiment, and you could see, yeah, it's quite consistent. Okay, that's almost the end. So once again, 4 major contributions. We implemented an integrated task scheduling and offloading in our already existing orchestration platform, which was only supporting service placement so far. But task offloading scheduling is a broad topic, it's quite relevant. There are plenty of solutions out there that could be evaluated in real world environments. For that, we provide a universal and general and flexible model of tasks. We allow to integrate already existing applications, and finally, we support, as for service placement, automated standard evaluation with metrics for task scheduling and offloading. And yeah, this was an empirical evaluation with first insights on the overall overhead. Then, of course, there are limitations. So the integration is only possible via MQTT and HTTP so far. We have a centralized, cloud-based orchestration, but this is purely the majority. So if you look at the literature, most of the Cloud Edge platforms are using centralized components, but there is the possibility to introduce some decentralized organizations. So for example, you could also submit tasks directly on the exposed RESTful API of the node agent we developed. This is required because we implement everything using the open fork reference architecture, and it's required by this reference architecture, well, to have some decentralized functionalities. And of course, for the experiment, a minimal cloud edge topology was used. Yeah, so that's it. And if you're interested in, everything is available on GitHub, the source code, the orchestration reports. There's an OpenEye specification for all RESTful interactions that are necessary, and also deployment scripts for Kubernetes if you want to try it out. Here's the QR code. Just type in the link. Yeah, that's everything from my side. Thank you very much, and I'm happy to answer your questions in the poster session. Thank you.
Thank you.